But ṣé okay mi ò lè short ẹ̀ down bí. Máa kọ̀ fílẹ̀ tó bá ti lọ live, I will leave it.
But the way I saw the thing on my phone that time, we different from what's the door.
Okay, ẹ wo nǹkan tó gbé wa ṣó ti lọ nìyẹn.
A number of years
Ó ti
ago,
lọ nìyẹn.
an American student family in Europe.
So ẹ jẹ́ kí n lọ
We are back on now.
It's on now.
Is it using your account?
No, tí wọ́n ní.
You can do it on your own.
Ó lè gbé wọn rí ṣe.
You see?
Báwo ni mo ṣe máa make wọn host padà kan máa bá ṣe wọlé?
A man explained that he lived in America. He said that for over a year he worked as a farmer in Oklahoma.
Make host, beg.
He planted tomatoes and
Yes.
melons.
Okay.
It was, the man said, the
So
happiest
I just
time of his life.
Have you opened the account before?
Prisoner.
So báwo ni mo ṣe fẹ́ rí link yẹn sà tí màá lè send YouTube link bẹ́ẹ̀ ni YouTube link òun ọmọ yẹn máa lọ join.
To welcome them to the golden
Ká lórí laptop ni I would have seen it. Ó yẹ kí n play ẹ̀ bí àbí. Or what do I do?
to an opportunity.
Actually, what I expect is that when they try to log into the Zoom and it's full, it will direct them to that
YouTube, yes. Normally.
But the one now,
Okay, ẹ jẹ́ kí n wo.
the one protect
Ṣé share ní kí ni?
sure. They say even after the class, they can always go to YouTube too to. Yes, sure.
After the class, yes.
Yeah.
Because they understand in a special way
And
how
let's
glorious it is to be an American. They renew our pride and gratitude to the United States of America.
Adeloye
The
and
greatest, freest
kí ló
nation,
lóko sọ dín ní Odùmọ̀ṣù.
the last best hope of man. on earth.
That's what Trump is trying to destroy. Reagan is saying that America draws its strength from people that come from all over the world.
Okay. Yes.
We shall see.
Iṣẹ́ ìmọ̀ pé ìgbà mi máa ń wà. If God has not sent a Pharaoh to destroy a nation, òun lọ̀rọ̀ US. They are just not serious.
Who is your job brother? I want to contend with the Sifa. He's Sifa contesting.
He's subdued. Ojogbo is not serious.
Who is it?
He's on this academy for Nana. He's always causing trouble. He's always called. You see him sending and.
No, would you vote for anyone of them? You know Ojogbo. You know. I know him.
I know Ojogbo.
He has already described him.
He's a troublesome maker. Too troublesome for my liking. Too troublesome.
And when he sees you, greet you well.
He's playing complexion now. He came to ASU Congress the last time.
I mean, I know him, but I don't know him. I don't know the name.
It was the Akadabra that made me to know him.
I'm going to vote for the man that told me first. It was Safa that told me first.
It was Shifa I knew first too.
To me, it was Dr. Shitu.
Shitu, the occurrence of Dean in social science.
This again now.
Dr. Shitu in that the wife died last year.
Did the wife die? This one is in economics. So.
Is there something now? The wife died last year.
So let us consider the conservation of linear momentum. If the net force acting on the body is constant, then the time rate of change of linear momentum is zero. That is the PDT, because where P is the linear momentum of the body. If the PDT is zero, that means that P is a constant. And this could be linked to Newton's first law. So when two bodies are involved, that is, if only one body is involved, what you have just P is equals constant. Since it's the only body involved, P equals mv, it means that V is constant if the external force is zero. So when two bodies are involved and there's no external force on the system, then the PDT, which is the dT of M1 V1 plus M2 V2, must be equal to zero, which I denote the velocities at a later time by prime. Put another way, M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. We are assuming that M1 remains M1 at a later time, and M2 remains M2 at a later time. If we rearrange, you see that M1 into V1 prime minus V1 equals minus M2 into V2 prime minus V2. These are the changes in momentum of each of the bodies. So what's our conclusion then? The momentum lost by one is gained by the other. Let's see an example of this. There are two types of collision, elastic and inelastic. Let's see what elastic collision is. In elastic collision, both the linear momentum and the kinetic energy are conserved. Thus, M1 V1 plus M2 V2 equals M1 prime, M1 V1 prime plus M2 V2 prime. That's conservation of linear momentum. What about kinetic energy? The law of conservation of kinetic energy will imply that M1 V1 squared plus M2 V2 squared equals M1 V1 prime squared plus M2 V2 prime squared. We look at equation 3.4. Let us rearrange. M1 V1 minus M1 V1 prime equals M2 V2 prime minus M2 V2. Or M1 into V1 minus V1 prime equals M2 into V2 prime minus V2. Then the other equation, M1 V1 squared, is rearranging that one as well. And as M1 V1 prime squared equals M2 V2 prime squared minus M2 V2 squared, which you can write as M1 into V1 squared minus V1 prime squared equals M2 into V2 prime squared minus V2 squared. We divide one by the other. This the last two equations. Divide the second one by the first one. Well, divide 3.7 by 3.6. And then you apply difference of two squares. You're going to get V1 squared minus V1 prime squared over V1 minus V1 prime equals V2 prime squared minus V2 squared over V2 minus V1. We have not applied difference of two squares now. We just divided by 3.7 by 3.6. If you now apply difference of two squares, we're going to find V1 plus V1 prime equals V2 plus V2. V2 prime plus V2. That's equation 3.8. If we rearrange that equation, we get V1 minus V2 equals V2 prime minus V1 prime, which you can write as minus, bring out minus, bracket opens, V1 prime minus V2 prime. What do we have on the left? That is the speed of our approach, and on the right is the speed of separation. From equation 3.8 then, V2 prime equals V1 plus V1 prime minus V2. Can you see that? Just rearranging equation 3.8. If we put this into equation 3.4, that is M1 V1 plus M2 V2 equals M1 prime, M1 V1 prime plus M2 V2 prime. We are going to arrive at M1 V1 plus M2 V2 equals M1 V1 prime plus M2. Instead of writing V2 prime, we just import that last equation, that is V2 prime equals V1 plus V1 prime minus V2. Put it into that expression, and then what you get is equation 3.10. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V1 plus M2 V2 V1 prime minus M2 V2. If we make V1 the subject of the formula, then M1 V1 plus M2 V2 minus M1 minus M2 V2 minus M2 V1, please. plus M2 V2 will be equal to M1 V1 prime plus M2 V1 prime. Just take the terms without prime on the right in equation 310 to the left. Now on the right now, V1 prime is common. So you are left with M1 minus M2 V1 plus 2M2 V2 equals bracket opens M1 plus M2 V1 prime. So divide both sides by M1 plus M2. We're going to arrive at V1 prime equals M1 minus M2 by M1 plus M2, all that multiplying V1 plus 2M2 by M1 plus M2 multiplying V2. By symmetry, V2 prime equals M2 minus M1 by M1 plus M2 V2 plus 2M1 by M1 plus M2 V1. What do I mean by symmetry? If you look at the equations for both linear momentum and kinetic energy, notice that M1, V1, M2, V2 are symmetric in the expressions. So once you have got any of them, you can easily get the other one by making the appropriate substitutions. Just swapping 2 for 1 and 1 for 2. Look at V1 prime. M1 minus M2 by M1 plus M2 V1 plus 2M2 by M1 plus M2 V2. Because of the symmetry, V2 prime equals just swap 2 for 1 and get your answer. Just like Pythagoras theorem, you know, opposite squared plus adjacent squared equals hypotenuse squared. So you can swap O and A because that equation is symmetric with respect to O and A. That is why it does not matter as far as Pythagoras theorem is concerned, which one is opposite and which one is adjacent. Now, if M1 equals M2, it means that M1 minus M2 is 0. If that were to be the case, then V1 prime will be equal to V2, and V2 prime will be equal to V1. What that means is that the masses simply exchange velocities. See, V2 be equal to V1 prime, and V1 is equal to V2 prime. It also means that if one was initially stationary, the other one becomes stationary after collision, having exchanged its initial velocity with the one that was stationary. And let us look at inelastic collisions. When the collision between two bodies is not elastic, the total linear momentum of the system is still constant. So that is always conserved, but the total kinetic energy is reduced. Indeed, there's a period of compression and a period of restitution. The latter period is that in which the bodies recover their shapes after the initial compression. Take a look at two bodies, M1 and M2, even though not indicated in the diagram. The one on the left is M1. M1 has initial velocity U1, and M2 has initial velocity U2. Thus, M1 U1 plus M2 U2 will be equal to M1 V1 plus M2 V2. This is the only law of conservation that applies in this case because the collision is inelastic. Let's look at the kinetic energy. Half M1 U1 squared plus half M2 U2 squared must be greater than half M1 U1 squared plus half M2 U2 squared. That is, total kinetic energy before collision must be more than the total kinetic energy after collision because some energy must have been lost, some kinetic energy must have been lost during the collision or because of the collision. The coefficient of restitution is defined as the speed of separation of particles, whereas the speed of approach of particles, and it is denoted by the letter E. 0 is less than or equal to E, which is less than or equal to 1, with the limits corresponding to completely inelastic collision, in which case E is 0, and the two bodies stick together after collision, and completely elastic when E is equal to 1. In the figure above, U1 is greater than U2. Figure is missing. Let's consider two bodies, one in front of the one to the right of the other. If the one in front is moving faster than the one behind it, will there be any collision? There will be no collision. The speed of approach is U1 minus U2. I will modify this slide before sending it to you. The speed of separation is V2 minus V1 because V2 must be greater than V1, as I said earlier, or they will not separate. That is after collision. V2 must be greater than V1. Then E is V2 minus V1 over U1 minus U2, which is greater than or equal to 0. Example, find the value of E if M1 travels towards the right at 6 meters per second and M2 is at rest. And after collision, M1 travels to the right at 2 meters per second and M2 travels to the right at 4 meters per second. Those are the two bodies. M1 has initial velocity 6 meters per second. M2 has initial velocity 0 meters per second. And after collision, M1 has velocity 2 meters per second, while M2 has velocity 4 meters per second. Both still moving to the right. Then E is 4 minus 2 over 6 minus 0. What you get is 1 over 3. 2. Find the value of E if M1 travels towards the right at 4 meters per second and M2 travels at 2 meters per second towards the left. And after collision, M1 travels to the left at 1 meters per second and M2 travels to the right at 3 meters per second. That is the diagram. E is going to be 3 plus 1 over 4 plus 2. And see why the velocities are, why you have plus 1 and plus 2 in this case. Because the bodies are moving to the left. The coefficient of restitution is 2 over 3. Another example, two particles A and B of mass 2.2 kilogram and 0.5 kilogram, respectively, are moving towards each other along the same straight line on a smooth horizontal table. Particle A has speed 12 meters per second and B has speed 2 meters per second. Given that the coefficient of restitution for the particles is 0.2, find A, the speed of A and B after the impact, and B, the total mechanical energy of the system before and after impact. Before impact, that's the diagram. After collision, that is the diagram. We don't know what B1 and B2 are. On the law of conservation of linear momentum, M1U1 plus M2U2 plus M1V1 plus M2V2. Rearrange that, you are going to arrive at 2V1 plus 5V2 equals 14. And the current restriction is going to be speed of rotation of particles or speed of approach of particles, which is E. You know, E is half. It means that V2 minus V1 over U1 minus U2 is 1 over 2. Therefore, V2 minus V1 is 7. From this equation, and then star, which is V2 minus V1 equals 7. Solve this equation simultaneously. You arrive at V1 being equal to minus 3 meters per second, and V2 equals 4 meters per second, meaning that each particle reversed after the collision. The kinetic energy before collision is half into M1 U1 squared plus M2 U2 squared. Put all that together, you arrive at 15.4 joules. What about after collision? You get 4.9 joules. Hence, the loss in energy is 10.5 joules. What happens to the lost kinetic energy? It's converted possibly into heat, sound, or some other form of energy. I think that as an exercise. The small smooth sphere A of mass 2 kilograms is traveling along the straight line on a smooth horizontal plane, speed 6 meters per second. When it collides with the small smooth sphere B of mass 3 kilograms moving along the same straight line in the same direction with speed 2 meters per second. After the collision, A continues to move in the same direction with speed 2 meters per second. Find the speed of B after the collision. Find the coefficient of restitution between A and B, and state any assumption you made in your calculations. Work and energy. The work done by a constant force F over a displacement X is the dot product of the two vectors. So W is F dot X. W of course is a scalar, so it should not be bearing, it doesn't have a bold face. It's not bold because just the font that's looking to look at it. Thus, the work done by a force is a scalar. We can also write equation 5.1 as W equals Fx cos theta, where theta is the angle between F and X. Yes, we can also write equation 5.2 as W equals F into X cos theta, because conclude that if we indeed define the work done as magnitude of the force times the component of the displacement in the direction of the force. The other, I'm familiar with that one. The one you are more familiar with is the next one. Okay, that's the one you're familiar with. Force times distance moved in the direction of the force. On the other hand, this is the one you're not familiar with. We could write W as being equal to F cos theta times X. That is, the work done is the magnitude of the force times the component of the force in the direction of the displacement. Right, that should be the magnitude of the displacement times the component of the force in the direction of the displacement. That is the magnitude of the displacement, which is X, times the component of the force. The component of force in the direction of the displacement is F cos theta. Note that in figure 5.1, cos theta is W over F. First, also missing. I will get all this sorted out before you get. Cos theta is just the opposite by the adjacent over the hypotenuse. So Z is the opposite, F is the hypotenuse. Okay, that's it. That's figure 5.1. Z is F cos theta. So cos theta is going to be Z over F, adjacent over hypotenuse. Adjacent is the bit between the right angle and where the head of the force hits the horizontal as shown in the figure. Unit of work is the joule, which is the product of the Newton and the meter. So the unit of force, that is the joule, can be seen as Newton times meter. Example, find the work done by the force -1, 2, -2 when it pushes a box from 0, 1, 2 to 2, 1, -3 meter. The solution is the force is -1, 2, -2. The resistance is 2, 1, -3, -1, 2, -2. That is final position minus initial position. What you get is 3, -1, -1. Because the work done is the dot product, which is -1, 2, -2, dot 3, -1, -1, which will give you -3 -2 plus 2, which is -3 joules. That is the work done by a constant force. What if the force is variable? Then we can only talk about an element of work being done by the force over an element of displacement. We shall write that each of these as very small because the force is not constant. We are assuming that over a small bit of displacement, F is constant enough for us to say, okay, the elemental amount of work done is equal to that force multiplied by the small distance or displacement to give us equation 5.5. Then the total work done is the integral of equation 5.5, that is from 0 to the work done W. We're adding little bits of the W on the right hand side from x naught to x of F dx. Where x naught is where the work done was 0, and by the time we got to x, the total work done was already double. Let us look at special cases. Gravitational force. In the case of gravity, the force is constant and always directed towards the center of the earth, and it is the weight of the body. So Fg equals minus mgj, minus because it's pointing down. Where j is the unit vector in the vertical direction directed upwards. And see, that is why Fg is minus mgj, that is mg, but in opposite direction to j. The work done by this force over a displacement hj, h being positive means the displacement is in opposite in direction to the force. So positive h means that the displacement is up, and you know g is down. It means that the displacement is opposite direction of the force. Wg will then be equal to minus mg8. Though the angle between them is 180 degrees. Cos 180 is minus 1. That is mg times h cos 180. Cos 180 degrees is minus 1. That's why w equals minus mg. Thus, gravity does negative work when the motion is upward. Though gravity is pointing down, the body is moving up. So displacement is in the opposite direction to the force. When the motion is downward, say minus hg, the work done is mg, which is mg, because the angle between the force and the direction of the displacement will be 0. And cos 0 is 1. So wg is just equal to mg8. So positive work is done by gravity when the body is dropping in the field of the earth. Let's look at the elastic force. Of course, if a body is later you see this is work done by gravity. The work we do will be opposite in this. Opposite to this work. So when the body is being lifted up, you'll be doing positive work. When it is coming down, you'll be doing negative work. Why is it impossible? Why are you doing positive work when you are moving the body up? So it's because the force you are applying is directed upwards against gravity. So you are pulling the body up, and the body is also moving up. So the force you are applying is in the same direction as the motion of the body. So the work done is positive. But if you are coming down, you are lowering the body. The force you are applying is still upward, but the displacement is now downwards. So the work you are doing is negative. So when you are doing negative work, gravity is doing positive work, and vice versa. Let's look at elastic force. The force in this case is governed by Hooke's law, F equals minus kx, since it is a restoring force. In other words, if you stretch a spring, the spring tries to return to its original length. If you stretch a spring or compress a spring, the same applies. The work done by the elastic body is therefore WE, is integral from 0 to x of f dx. It is integral from 0 to x minus kx dx. Carry out that integration, you get minus half kx. We have suppressed the arbitrary constant in this case because since it is potential energy, we can choose our initial potential energy. We can choose our datum that, or rather, reference potential energy as 0. It does not matter whether it is stretched or compressed. The force experienced by the body is always against the force acting on it. Why is that so? Look at x squared. So whether x is positive or negative, by the time you square it, it becomes positive. So equation 5.11 on the right, we always give you a negative value. Whether x is positive, whether it's a compression or whether it's an extension or a compression. Energy. The energy processed by a body is its ability to do work. It follows that the unit of energy is also a unit of work. That is the joule. Work done by a body, done in the body, is stored as energy. Now, kinetic energy of a body is the work it does on account of its motion. The work done by a body of mass m in moving through a distance dx is the W equals f dx, which is, but we know f is ma. So that will be ma dx, which is m. A is 7, which acceleration is dv dt. So m dv dt dx, which is m dx dt dv. Just rearranging that term, which is then equal to mv dv. Hence, the work done from 0 to w, 0 from 0 to w of dw is w, which is 0 from v0 to v of mv dv, which is half mv squared from v0 to v, which is half mv squared minus half mv0 squared. This is the change in kinetic energy of the body when its velocity changes from v0 to v. Therefore, the work done on a body is equal to the change in the kinetic energy of the body. Let us now look at the work done by conservative force. And then, in view of that, we are going to define potential energy, because it's only when you have a conservative force that we're talking about potential energy. A conservative force is such that the work done in a cycle is 0. It also means that the work done does not depend on the path taken. The mechanical energy of such a system is conserved. Thus, we can write ma equals Ke plus P equals constant. If the change in kinetic energy is written as delta K and the change in potential energy as delta U, then delta K plus delta U must of necessity be equal to 0, or delta K equals minus delta U. So from the work energy theorem, delta W equals delta K. So delta W equals minus delta U. Equation 516, 517. Or more precisely, the W equals F dx, which is minus du. If you go to the limit as delta W tends to 0, which also means delta U tends to 0, it becomes the W equals F dx, which is minus du. Therefore, F equals minus du dx, where U is the potential energy function. The student can then show that W minus W naught equals integral from x naught to x of F dx, which will be U at x naught minus U at x, where U is a function of position only, as you can see. And of course, if x equals x naught, then W must be equal to 0. Again, stressing the fact that when the force is conservative, the work done in the cycle is 0. Because if x equals x naught, that means you have gone a full cycle. Indeed, only in this case does a potential energy function exist, as I said earlier. And then that's when a potential, you can define a potential and start talking about potential energy. And then write equation 514 as Ke plus U of x equals 514. Ke plus P equals constant. Ke and P is U of x equals where U of x depends on the nature of the problem. Kinetic energy is always half mv squared. Hence, we can write equation 522 as half mv squared plus U of x equals E. Equation 521 is W minus W naught equals all that stuff. But U of x will be equal to 0 from x naught to x, f dx plus U of x naught. As we said earlier, we can arbitrarily choose the value of U of x naught, and therefore, without loss of originality, we can choose our x naught conveniently and set U of x naught equal to 0. For example, when dealing with the body falling in this class, we can set the floor equal to x naught, and then you can take the potential energy of a body as 0 if it is on the floor. That makes plenty of sense. On the other hand, we can also set the center of the earth as the 0 of potential energy. In any case, we can always write equation 524 as U of x equals minus integral of from x naught to x of f. Yes, the minus sign multiplied by the work done by the conservative force. Let us consider again the two examples as well. One, gravitational force. In the case of gravity, the force is constant and always directed towards the center of the earth, and is the weight of the body. Here is the unit vector in vertical direction directed upwards. The work done by this force over H is, we have seen that before. Because gravity does negative work when the motion is upwards. You just want to see how this ties in with our U of H. So U of H equals minus integral from H naught to H of minus mg dy, because F is mg. F is minus mg because it's pointing down, then dy. You get mg into H minus H naught. Bear in mind that going up means that H naught is less than H. Because the potential energy of the body increases as it goes up, as we expect. If we set the Earth's surface equal to 0 potential energy, then U of H equals mgh. The formula you have been so familiar with from your O level days. When the body rises from height h naught to height h, delta U equals mg into h minus h naught. When the kinetic energy reduces, delta K equals half mv squared minus half mv naught squared. Of course, that means the body must have slowed down, so that v squared will be greater than v naught squared. Delta K plus delta U equals 0, so we can write half mv squared minus half m v naught squared plus mgh minus mgh naught equals 0. Therefore, half mv squared plus mgh equals half mv naught squared plus mgh naught. My motion is downwards. Say minus hg. The work done is mgh, which is U of h will then be equal to minus integral from h naught to h mg dy. We get minus mg into H minus H naught, which is mg into H naught minus H. The positive work is done by gravity when the body is dropping in the field of the air, but this constitutes a fall in the potential energy of the body. Hence, H is less than H naught. This is equal to minus mg. We take the surface of the earth as H naught equals, yet again, when the body falls from height H to height H naught, theta U will be equal to mg into H naught minus H. Means that the kinetic energy must increase as mv naught squared minus half mv. Must have lost a little bit of the recording. V squared equals V naught squared minus 2d into H minus H naught. If H naught is lower than H, then body is rising, and you get V squared equals V naught squared minus 2g delta H. However, if you set H naught as the top of a building, say, and H a point lower than H naught, then V squared equals V naught squared minus 2g to H minus H naught. Put all that together, you arrive at V squared, V naught squared plus 2g delta. We call these two formulas in level physics, of course you do. 2. Elastic force. In this case, F equals minus kx. Since it's a restoring force, in other words, you stretch a string, but we have seen that before. The work done is minus half kx squared. Using energy U equals half kx squared. Hence, we can write half m v squared plus half kx squared equals E, where E is a constant. We consider 2 points then. Half m v squared plus half kx squared equals half m v naught squared plus half kx naught squared. An example, a ball drops from the top of a building, 10-meter tall building. Find its velocity halfway down. Do it yourself. The catapult is stretched 0.2 cm. If the stiffness constant is 250 newtons per meter, find the velocity of the stone of 20 grams when released. I think we can take all this. I will send some tutorial questions. We're scheduled to meet on Thursday. Let's see how. We do have a wonderful day.